For starters, we are required to have this disclaimer. Contrary to popular belief, any similarities to actual people or events are purely coincidental.
Hi everyone, I'm your lecturer for the theory of continental drift and complete tectonics. Today we'll be learning about the Wegener-du hypothesis. This is the concept that continents have undergone large-scale horizontal movements relative to another and the ocean basins over geologic time. Early proponents of this concept was Bacon in 1620, Humboldt in 1800s, Antonius Nieder in 1850s, and F.D. Taylor in 1910. However, Alfred Wegener, a German meteorologist, made the most convincing and propelling hypothesis in 1915. Like any good science experiment, we should support the hypothesis with evidences. Am I right? And yes, he presented his hypothesis with solid evidence. So Wegener, what is the theory? My theory is that all the continents were once joined together in one super large continent called Pangaea. Remember, it's called Pangaea. When did that happen? Around 225 million years ago during the Jurassic period. You know the Jurassic Park where the supercontinents began to break up and fragments start to drift away. I will call this the continental drift. In 1937, Du Toit modified the hypothesis and suggested existence of two large continents after the first breakup of Pangaea. Number one, the Laurasia and Gondwanaland. I will classify all the evidence of this theory into 6 groups. Number 1, continental repeat evidence. Continents fit nicely when they are joined together like a puzzle piece. Shoreline and continental shelves of several continents matches. Examples will be North America and Europe, Africa and South America. Number 2, structural evidence. This refers to the continuity of structural landforms in continents now separated by oceans. For example, there's a matching of shoes of 4 mountains in Africa and in South America. Number 3, lithological evidence. The same type of rocks can be found on opposing sides of the boundary separating 2 continents. For example, Australia and India. Permian rocks can be found. Permian rocks which are around 230 million years can be found on these 2 continents. Number 4, paleomagnetic evidence. Magnetic orientation to the poles acquired by rocks at the time of formation is frozen into the rock. Today, the magnetic orientation in each continent shows a variety of angles to the Earth's present magnetic field. For example, they are all pointing in different directions instead of pointing all to the North Pole. This means that they must have shifted. Number 5, paleoclimatic evidence. Certain rock types form under appropriate conditions and their distribution is restricted. These rocks are later found in regions where they are unlikely to have been formed. How could this be? This indicates that the continents on which the rocks have rested upon must have drifted. For example, limestones and caroline can only be found under warm climates near the equator. Caroline rocks have been discovered within the present day, within the Arctic Circle. Number 6, paleontological evidence. This is the study of ancient species of life through the medium of fossil evidence. Fossils of ancient species of life can be found in continents now separated by oceans, at least a few thousand km. Mesosaurus was a small aquatic reptile whose fossils can be found within a limited zone of South America and Africa. It is unlikely that a creature could have swam across these thousands of km. The conclusion is that the continents must have been linked. This evidence effectively supports Wegener's theory of continental drift. However, there's a weakness of his theory. He has based his theory on the fact that continents are able to drift through the ocean floor. This was dismissed as impossible as the continental plate boundary is rigid. There was a lack of mechanism to enable huge rocks of continental crust across thousands of km on the ocean floor. The lack of technology prevented the verification of this idea. A few decades later, after technology becomes more advanced, the idea of continental drift
was revived
and discussed as plate tectonics. From the 1950s onwards, new discoveries, especially from the study of the ocean floor, led to new concepts. Among the new discoveries were the fact that oceanic crust is thinner and younger than the continental crust. Number 2, the fact that Earthquakes occurred in well-defined linear areas. And number 3, the ocean basins are divided by a great mid-oceanic ridge around 84,000 km long and 1,500 km wide. All this evidence have prompted Hess, a noted geologist, to propose a theory of seafloor spreading in 1960. I even interviewed him when he was having a holiday in Hawaii. So Hess, where did you get your inspiration? When I went to the kitchen to get my cup of hot coffee from the kettle, I saw an ant, that irritating ant. So I decided to take a spoon and then I scooped it up. However, it tried to swim. It appeared to me that it can swim. Then, voila! I took up the suggestion of convection current and added to my theory. Oh my god, inspirational. Thank you, Hess. Ocean floors are spreading apart, propelled by thermal convection current in the mantle, and are moving away from the ocean ridge. This is the ocean ridge. This continuous spreading produces cracks and fractures in the crust. New crustal rocks will be injected in cracks, then cool, and then spreads away from the center. This is how seafloor spreads and gets bigger. The spread of the seafloor cannot go on and on. The Earth will need to expand to accommodate the increasing size of oceanic crust, which is impossible. As oceanic crust cannot be indefinitely created, it must be somehow returned into the mantle. I propose that deep-sea ocean trenches were the zones that the crust was being thrust back down into the mantle, melted and reabsorbed into the mantle. This is deep ocean trench. Look at a piece of evidence to support the idea of seafloor spreading. Shallow earthquakes and volcanoes are found in mid-oceanic ridges. Geothermal heat flow is the highest over the mid-oceanic ridge. This means that rising magma from the ocean floor sediments are thicker as it is closer to the ridge. The rocks are also younger when they are closer to the ridge. This supports the idea that the mid-oceanic ridge is indeed very young and the ocean floor spreads away from the ridge. Deep-sea drilling confirms the depth of the sediment was related to the distance from the ridge. As the distance from the ridge increases, the age of the oceanic crust increases. So this part of the oceanic crust will be older than this part of the oceanic crust. Bai and Matthew presented conclusive evidence for the mechanism of seafloor spreading in particular. The oceanic crust revealed symmetrical patterns of magnetic strips of normal and reverse polarity on either side of the ridges. As magma emerges from the side of the ridge, it is orientated to the Earth's magnetic poles during that time, before they are cooled. When the Earth's magnetic field changes reverse polarity, every 100,000 years, the magma will be oriented in another direction. This proves that the theory of seafloor spreading is true. All these evidence support the theory of plate tectonics. Okay, that wraps up for the theory of plate tectonics and continental drift. I hope you have gained new insights and understand the topic better. Ta-ta! Number 2.